So this is my lecture 9. This is my lecture 9. So in the last class, we designed 2 degree of freedom controller, sorry, 1 degree of freedom controller, and we saw that the roots of the polynomial h's, that is the controller zero polynomial, affects the reference input to output characteristics as well as the control effort characteristics. That means the peak in reference input to output may occur if the roots of the controller zero polynomials are close to the imaginary axis. So this closer imaginary axis zero location also will cause high control effort or large peak in control effort. So now we will see how to avoid those two things using a 2 degree of freedom control. 2 degree of freedom controller. First we will see what is 2 degree of freedom controller, then we will see how those limitations of 1 degree of freedom control can be taken care of. 2 degree of freedom controller. So this is the block diagram of 2 degree of freedom controller. So this eta is your noise, measurement noise, and D is your output disturbance or process noise. So now you see the difference between 2 degree of freedom and 1 degree of freedom control. So here HS, QS, and KS are polynomials, and CSAs are also polynomial. So here this is your plant, and this is your 2 degree of freedom controller. This is your 2 degree of freedom to DOF controller. Now what is the difference? So you can easily see that here the measurement output and the reference input are are being treated in an independent way. In case of 1 degree of freedom, what happened? In case of 1 degree of freedom, controller was CS, that is HS by KS. So, and in that case, the only one input was going to the controller, that is tracking error. But here you can see that R and Y input are going, and those R and Y and those are treated independently because of the presence of Q and H, and as Q and H, so if Q and H are same, that means again that in that case this Q and H you can absorb, and it will be ultimately HS by KS, and in that case again tracking input will go to the controller, only one input. So as QS and HS are different here, so that's why this 2 degree this is 2 degree of freedom control. In the because here reference input and output are being treated independently. So in case of 1 degree of freedom control, QS equal to HS. So that only one input will be there to the controller, that is tracking error. Got it? So I am writing here DF control R and Y are independently treated since HS not equal to QS. If so, in case of 1 degree of freedom control, so HS equal to QS. So that means 2 degree of freedom is a superset of 1 degree of freedom control. Okay, so the main difference is that here the operator QS and HS are different. Operator QS, which is operating on reference input, and the operator HS, polynomial operator, on which is operating on the measurement output. So this is your measurement output. So they are treated independently. But in case of 1 degree of freedom control, what is happening, since QS equal to HS, so they will be treated in a similar way. They are not independent. In that case, only error or tracking error input will be going into the controller, because Q and H you can absorb inside this block, and it will be ultimately H by HS by KS, or you can write QS by HS. And in that case, only the error, only the input to the controller will be your tracking error. Okay, so I have written in case of 1 degree of freedom, HS equal to QS, and therefore the input will be, input to the controller is R minus Y equal to error, tracking error. Okay, so this I have written. This is an important information. So now for an mth order controller, for an mth order 2DF controller, so what is your KS? KS is a polynomial. So KS will have mth order polynomial s to the power m plus km minus 1, s to the power m minus 1, plus after dot plus k1s plus k naught. And HS, it will be hm s to the power m plus h m minus 1 s to the power m minus 1 plus after dot plus h1s plus h naught. And here QS, so QS is qm s to the power m plus qm minus 1 s to the power m minus 1 plus after dot plus h1, sorry, q1s plus q naught. So you can see, so here Ks is monic polynomial, because the highest order coefficient is that means km is equal to 1. So that's why k is also called monic polynomial, but these are not monic polynomial. So here additional thing, so additional polynomial is QS, and when it is 1 degree of freedom control, then QI will be equal to HI, and you can and in that case you need not to represent it as separately, and you can absorb inside. Now naturally the question is how to realize such a control, because ultimately HS and QS are polynomial. So if you independently represent HS and QS, it will be differentiator, purely differentiator, higher order differentiator. So physically it will not work. So then how to represent this such a control law in a minimal fashion? So the block diagram, this block diagram of this controller is well known. So the realization of a realization of a second order, first of all, second order 2DF control. That means in that case m equal to 2, second order. So first, so it can be represented in a observer canonical form. I think this is not observer canonical form. It is not yet taught. It is not there in your course, but you can easily verify the block diagram that I am drawing, that your controller will be, for that block diagram your controller will be u equal to 1 by uh, 1 by u will be equal to hs by ks into y plus eta s into y plus eta s plus qs by hs into rs. So this block diagram I am just drawing. You please verify it whether you are getting that transfer function or not. This has some rule. That rule I am not telling here because this all the things related ideas you do not know. So this is taught in control theory class, that is in higher level for MTech students. You can also take as elective later. So this, as it is a second order, so two indicators are needed. So I am drawing two indicators, and then so two indicators I have drawn. Now this blocks I am drawing. So this is suppose your minus h0 minus h1 minus h2, and this is suppose y plus eta. And here k1 minus k1, of course, minus k1. This is your u controller output. This is minus k1. This is minus k0. And then this is R line R. This is your Q0, and then this is Q1. This is Q2. Okay, so please verify that you are whether you are getting this one or not. This controller u will be equal to here. U will be equal to h2s square plus h1s plus h0 divided by s square plus k1s plus k0 minus this into y plus eta plus q2s square plus q1s plus q0 divided by s square plus k1s plus k0 into r. So please verify this. So verify this. So this is also known as observer canonical form. This is also known as observer canonical form represent from Observe a canonical form realization. So here just I have shown that although these are polynomial, but in practice you can realize using op-amps or uh, using op-amps like this. Some are an integrator, some are integrator and gain block. Minimal realization. You can see this is only two integrators are required, so that's why it is a minimal realization. It is not so. So you may think about realizing this one and this one separately, but in that case, four indicators are required. But for minimal, since the order of this system is two, so only two so you have to have a realization such where only two indicators are needed. So this is such a realization. Now we'll see. Now we'll see. I mean, what are the important transfer functions we are getting as we have got in case of 1 degree of freedom, and then we'll see what kind of additional things, additional advantage we'll get because of setting, because of having this additional that means because of having qs not equal to hs, that means 2 degree of freedom configuration. So important transfer functions, some important transfer functions, some important transfer functions with 2df control. So small I should write 2df control. So what are those important transfer functions? The same important transfer function I have also obtained. For example, arc2y, arc2y, arc2y transfer function in case of 2D of freedom control will be what? y by r, ys by rs. This will be equal to, you can easily see here that it will be, if you see this arc2y transfer function, it will be just CQ divided by delta. Please check it. I'm not checking. This is, I have already seen. I've already done all these things. So please check it. This is CQ by delta. What is delta? Delta is AK plus CH. As and the last class. So in bracket I am writing with 1 DOF. With 1 DF, what we have got? It is CH by delta. Delta is AK plus CH. Now just the difference we want to see. What is your seconds? D2y transfer function. D2y transfer function is y by d. Y by d transfer function is here. You can easily see AK by delta. That means same as what 1 degree of freedom. Same transfer function we have got in case of 1 degree of freedom. D2y transfer function will not change in case of 2 degree of freedom. Similarly, eta to y, transfer function here, y by eta. Again, you will see it is ch by delta. So this is same as 1 DOF. So now, what is the last one? Last one that is important is control effort. Arc2y transfer function, sorry, arc2u transfer function. Arc2u transfer function will be u by r. U by r transfer function, you can easily verify that it will be AQ. It will be AQ. It will be AQ. Oh, sorry. This is blue. This will be AQ by delta. So this is using 1 degree of what we got. It will be AH by, it was AH by delta using what. So where delta equal to, again I am writing delta equal to AK plus CH. So here all are polynomial as, ks, cs, hs, delta s. So s term I am not writing for convenience. Okay. So now you see what is the difference. Difference you can see. Difference are observed only here and here. The other two transfer functions are same. So that means here, so advantage, what are the advantage you will get? So only the reference input to output characteristics are now changed. So here once controller, as you have seen, once this closed loop poles you have designed delta, then your q, your h will become fixed, h as well as k. Once the closed loop poles you will design the closed loop, once the closed loop poles you will choose, your h and k will be fixed. So now the question is how what kind of flexibility you will get because of this presence of q. So q is now in your hand. Q is an additional parameter. Q you can fix on your own. Okay. So the additional parameter, so advantage of. Now how to appropriately choose Q, that will come. So advantage of 2DF configuration. What is the advantage? So the advantage is that the additional polynomial helps achieve shaping, tracking characteristics, and controllable characteristics, effort characteristics better. Helps achieving the additional polynomial QS helps achieve superior achieve better helps achieve shaping of the additional polynomial QS helps achieve superior shaping of tracking characteristics and control effort characteristics. Okay, so because control effort characteristic, control effort characteristic with the same delta. So now suppose you want to have some delta is given. So once delta is given, in case of 1 degree of freedom, what will happen? Once delta, if you want to fix, if you want to have that delta, then h and k polynomial will get fixed. So once h and k polynomials get fixed, you do not know where the roots of the h's will lie. If the roots of the h's will be close to the imaginary axis, then what will happen? Then peak velocity will occur in R2Y characteristics, as well as the control effort peak will occur in the control effort peak will occur, control effort effort in the control peak in the control effort response will occur. So now since here what is happening here, because Q is in our hand, Q is an additional parameter. So Q I can choose on my own so as to have some independency in shaping R2Y characteristics and R2U characteristics. Got it? So here you write the presence of Q. The presence of QS helps achieve some independency in shaping R2Y and R2U behavior. While keeping the other behavior same as 1DF control. This is the thing. So here another important transfer function I forgot to write, that is Loof transfer function. What is Loof transfer function? LS equal to CH divided by AK. So here also using same as 1 degree of freedom. So in case of 1 degree of freedom also it is CH by AK. This means loop characteristics remain same, but the reference input to output characteristics and reference input to controller code characteristics, that you can have some independency, some in case of 2 degree of freedom control, because of this presence of Q parameters, this Q polynomial. Okay. So obvious other behavior, other loop behavior, I should write loop behavior. Loop behavior means here a disturbance function, but here you can see the reference input to output transfer function. Reference input to output transfer function in case of 2 degree of freedom, it will be different from 1 degree of freedom. Okay, reference input to output characteristics and reference input to controller code characteristics. So because of this presence of Q, actually this independency comes. So now we'll see how to design such a controller, how to choose. So choice of proper Q is very important. So choice of proper Q. So choice of a suitable Q. Now QS is your, how will you choose QS? So you can see so in practice how will you choose the QS? So choice of QS. So instead of choice of QS, I will just write directly. I will write directly design steps or design procedure, because the choice of QS is a major step there. Design procedure in 2DF control. Design procedure of 2DF control. So first is choice of first step is so in case of given reference model, so what is the problem? So given reference model, so what is given the reference to output model. So this model, the model matching actually you can achieve. So Ty to R, Ty to R characteristics, suppose this kind of characteristics given to you, alpha into Cs divided by delta hat S. Okay, so this is the reference model, reference input output model you have been given. So now how will you choose? So you can easily see, so from here, that in the reference input output model, the zero polynomial of the plant will be retained. Okay, and also the delta S order, delta S, so delta S order should be equal to, delta S order should be equal to order of AS. That means the relative order of TYR should be equal to the relative order of, at least more than equal to. So here I will write relative order of TYR should be more than I will write greater than equal to relative order of GS. Why? Now, because you can easily see what is your TYR. TYR is CQ by delta. So now you can see. So what is the order of Q? The order of Q is M. The order of Q is M. And what is the order of delta? Delta order is M plus n. The order of delta is M plus n. Yeah. Where n is the plant order. So the relative order of TYR is equal to the relative order of the plant, because here all the things are of same order. Relative order. So here QS, HS and QS, HS and KS I have chosen same. So normally what is happening? What happened? The order of QS you can choose less than M, but not greater than M. If you choose greater than M, then it will be improper controller. So relative order of this QS, the degree of QS should be less than or equal to M. Here, to have full flexibility, I have chosen M. So here, anyway, TYR transfer function relative order should not be less than GS. If it is less than GS means here improper. Here controller. If you want to have this less than GS, then ultimately you will have improper controller. Without improper controller, you cannot achieve TY to R transfer function. Okay, so this is your reference input to output model. So delta order of delta hat S equal to, I have chosen order of this one. So relative order. So here what I have chosen, relative order should be greater than equal to this one. Here we have chosen. Here we chosen. Here we choose. Here we choose equal to sign. Okay, here we choose equal to sign. Okay, so now this is your given reference input to output model. So this reference input to output model, actually a designer has to choose based on settling time, peak overshoot, all the specifications. So the designer has to choose. But remember that the poles of the plant, so the zeros of the plant has to be retained, particularly the non-minimum phase zeros. So if you non-minimum phase zero, if you do not retain here, then you cannot achieve that model matching using 2D of freedom control. So here this is another restriction, that is here I have chosen that the zeros of the plant we have retained in the TY2R characteristics. So this is relative order. Another thing is that the zeros of the plant, the zeros of the plant, fine, the zeros of the plant are retained in TYR. So otherwise, as I said, otherwise zeros. So RHP zeros should always be retained. RHP zeros should always be retained. Otherwise the controller will otherwise the desired model matching, the 2DF controller cannot be designed because it will be internally unstable. Because ultimately, if you do not consider the right half plane pole here, right half plane 0 here, and that means ultimately you are telling the controller to cancel right half plane 0. So if you want to cancel a right half plane 0, means right half plane pole 0 cancellation in a loop means it will be internally unstable. So right half plane pole 0 cancellation in a loop are not allowed at all. So this is your given reference input to output model. So this is first step 1. Choose. So the first one will be what? First one will be choose delta S equal to AK plus CH. This is equal to delta hat S into Q hat S. Where Q hat S is selected so as to meet loop performances. That means once this reference input to output model is given, means what? Your tracking characteristics, all these things will be fine as is desired. But then here what is your delta S? Delta S has to be chosen, like, because now Q hat S order is n. Q hat S order is n because that is equal to plant order. Now n plus Q hat order is what? Q hat order will be now delta S order is m plus n. So Q hat order will be mth order controller. So Q hat S is selected so as to meet. So here Q hat is additional. So delta hat is given to you. Now Q hat has to be chosen, and the Q hat is chosen such that you will get a desired loop shaping, desired sensitivity peak, and all these things. Then finals, and then second state set QS equal to alpha into Q hat S. So if you set like this, then what will happen? So this is the so there are three major steps. One is first you have to choose a suitable model matching, suitable model you want to achieve, and then so once suitable model you have achieved, given a plant transfer function CS and AS, you can achieve, you can have what is TYR based on your time domain specification, like settling time, peak overshoot, all these things. Then once this you have designed, so this you have chosen, so then what you have to do, you have to choose delta S, and delta S you will choose delta hat S into Q hat S, where Q hat S is selected, Q hat delta hat is given, and Q hat S is chosen such that some loop performance like sensitivity peak and disturbance, noise attenuation, all these things are obtained. Then ultimately Q set QS equal to alpha into Q hat. Now the question is why we will set like that. So if you do like that, then with the above design, what advantage you will get? What will be TYR transfer function? You can easily see. You can prove that. Now I will prove whether with this setting I am getting this transfer function or not. With this setting, you can see what is your TYR. TYR will be, let us see whether it is meeting or not. It will be CQ divided by delta. So that is equal to C into Q is what? Q is your Q you have chosen alpha into Q hat. Again delta you have chosen what? Delta hat into QS Q hat. So that means this will get cancelled. That means equal to alpha into C divided by delta hat. So that means that means same transfer functions as we wanted to have, that we are getting with this setting. That means that is we get the desired reference input to output model. So this is one thing. So second thing is that with the above design also you can see what is your TUR, that means R2U transfer function. It will be AQ by delta. So if you put A, what is now Q? What is your Q? Q is your alpha into Q hat. Now what is your delta? Delta is delta hat into Q hat. So that means, this means your T into UR. T into UR is A alpha into A divided by delta hat. So this implies control effort to output characteristics will be independent of choice of. This is very important result. This implies control effort characteristics, control input characteristics, control, actually this is reference input to control effort characteristics. This implies a reference input to control effort characteristics is independent of. So this is a very important thing, independent of choice of Q hat. That is Q. Q hat means Q, because alpha, how will you choose alpha here? So alpha is where? Here how will you choose alpha? Alpha equal to what? Alpha will be equal to t. For step input tracking, TYR0 should be equal to 1. So alpha should be equal to what then? Alpha should be chosen as such that where alpha is chosen such that T0 equal to 1, so that steady state tracking with respect to step input you can get step input. That means steady state tracking error will be 0 if TYR0 equal to 1. So alpha is chosen such that if you put C, so alpha into C0 divided by delta hat 0 equal to 1. That means alpha should be chosen as delta hat 0 divided by C0. So once alpha you have fixed, then what will happen? Once alpha you have fixed, so your TYR transfer function will be fixed. So this is your TYR transfer function, and not only that, this is very important. Your TU2R transfer function also will get fixed once you have chosen a desired reference model. So that reference input to output characteristics with this design method, the reference input to output characteristics and reference input to control output characteristics you can make unchanged while setting the loop performances. That means loop performance, disturbance attenuation, noise attenuation, and then sensitivity peak, robustness, all these things you can set little bit. You can get to your desired value by shaping by changing q hat. So if you change q hat, then all these things this will remain unchanged. So this is the beauty of 2D graph freedom control. So one example we will consider to illustrate this one. But remember that we will see this kind of unchanged reference input to output behavior and reference input to control effort behavior you will not get in case of 2 degree of freedom control. In case of 1 degree of freedom control, that we will see. So suppose GS is equal to 3 by S square minus S. So now can you say what will be the reference input to desired TYR? Desired reference input to output model will be what? So desired reference, so here relative order is 2. So T R2Y transfer function relative order also I should maintain 2. Also what will be the minimal order of TY to R that I can keep? That will be the order of equal to plan. As I have said here, the order of del S, the order of the minimal order of del S is equal to order of AS. So that's why here I will keep the this kind of second order model, say S square plus 2.4S plus 2.44. So why I have chosen this one, that I will come. But now you see what will be the numerator order. So in order to have, so here the relative order should be 2. Relative order should be 2 means numerator only one gain will be there. What will the value of that gain? That gain, so as to have steady state tracking means TY0 equal to 0. So TY0 equal to 0 is needed so that reference input will track the output without any steady state error. So it should be 2.44 so that DC gain of this transfer function TYR0 will be equal to 1. So now you can see that why I have chosen this one. So you can see note with this transfer function TYR exhibits peak overshoot, exhibit zeta equal to how much, exhibit zeta equal to, you can easily see, verify that zeta yields, TYR yields, zeta equal to, you can verify 0.768, which is a very good design value, good value as far as the system response is concerned. And settling time is how much? Settling time will be 4 by zeta omega n. So omega n you will get here 1.562, and then your ultimately settling time, this will be ultimately 3.33 seconds. So that means here we want a settling time less than 4 seconds, and zeta less than say 0.8, just near to 0.77. So this will obviously this will give a very good behavior of the closed loop system. So this is the reference input to output model I want to match, I want to have using 2-degree of freedom control. Then what is the flexible parameter mine? So now I have to choose Q hat S, a proper Q hat S. So first step is, in your design, the first step will be choice of a proper reference model. And then the second step is choice of Q hat S. And then third is the choice of, then QS will be known to you. QS will be this one. And then once delta S is completely known, then you can easily find what are the parameters of HS and KS using that Sylvester matrix equation that we have seen in case of 1-degree of freedom control. Okay, or Sylvester matrix equation, or using just computing just by comparing the coefficient for lower order system, you can easily do that. That I will be doing here. So this is your this is a TS, and then so now choice of Q hat S. Okay, choice of Q hat S. So choice of Q hat S. So there are three cases I will choose, and then we'll see the performance of the system. So case 1, suppose case 1, QS, roots of QS closer to j omega axis. Case 1, I'll choose, suppose, in such a way that the roots of QS closer to j omega axis. Let QS I have chosen like this, S plus 0.2. So if you choose S plus 0.2, then what will happen? So this will imply delta S is what? Delta S is delta hat S into Q hat S. So Q hat. So this means your delta S will be equal to, what is S square plus 2. Q hat S is what? Q hat S is equal to that, that is already given. So this is your Q hat S. This is your Q hat S. Sorry, this is a delta hat S. This is a delta hat S, and this is your alpha into CS. Alpha into CS. This is your alpha into CS. This is your delta hat S. Right? This is a delta hat S. Now you see, so this is S square plus 2.4S plus 2.44 into, what is your Q hat? Q hat is S plus 0.2. So this implies your desired Q hat delta S is if you multiply, it will come out to be like this: 2.6 s square plus 2.92 s plus 0.488. On the other hand, what we are getting, delta s is ak plus ch. So this implies again delta s will be equal to what? A is what? S square minus s. That is the Planck pole polynomial, given Planck pole polynomial. And here what will be the controller order needed? Your Planck order is your Planck order is 2. So controller order will be what? N minus 1. We have already seen. So m. So here I should write minimal order m should be n minus 1. Here I should write a minimal order minimum m should be equal to n minus 1, where n equal to Planck order. So that we have seen in case of 1 degree of freedom control. So here what will be then case? This is s plus k not first order control, because this is second order, plus cs. C is what? C is your 3. And what is your hs? This is h1s plus h naught. This will imply delta s will be equal to s cube plus k naught minus 1 into s square plus 3h1 minus h naught, sorry, h1 minus k naught into s plus 3h naught. So comparing 1 and 2, if you compare the coefficient of s to the power q, s to the square, s and s to the power 0, then you will get. So comparing 1 and 2, we get what? You can easily see that h naught will be equal to, please check, this is 1.163, then k naught will be equal to 3.6, and h1 equal to 2.17. So this means what is your hs? Hs is equal to 2.17 s plus 0.163, and ks equal to s plus 3.6. Now what is your qs? Qs equal to alpha into q hat s. Q hat s I have chosen, but what is alpha? So you can see alpha into cs equal to 2.44. So we get alpha into cs equal to 2.44. So what is alpha? What is your cs? Alpha into 3. CS is 3 equal to 2.44. So this implies alpha equal to 0.813. So then what is your QS? QS equal to alpha into Q hat S. So this implies your QS will be equal to how much? 0.813 into S plus 0.2. So this is one for a one choice of for a one choice of Q hat S. This is your QS, and this is your HS, and this is your KS. Now the question is whether one choice I have made, but I do not know whether with this choice the loop transfer function will look like what, or the whatever, the disturbance attenuation will be proper or not, or noise attenuation will be proper or not. All those things we will see. So the effect of this one. I know that T Y to R response will remain unchanged and U to R response will remain unchanged as we have derived. But what will happen to what will the impact of loop transfer function characteristics on your Q hat? Because ultimately if you change Q hat, then your what will so HS your if you change Q hat means your delta will change. So desired pole location will change. Desired pole location will change means H and K will change. H and K will change means your loop transfer function will change. So loop behavior will change. Although these two things TU to R and TY to R characteristics will remain same. So now we have to choose a suitable Q hat so as to have desired loop behavior as well. So for case 1, I have chosen roots closer to j omega axis. Now we will choose, that means low Q hat I have chosen. Now mid, some medium value I will choose. So case 2 I have suppose chosen. Then I will show the comparison. Case 2, suppose I have chosen Q equal to S plus 2. Now this is the roots I have chosen not too far away from imaginary axis or not too close to the imaginary axis. So that's why this is a medium value I have chosen. Here I have chosen that is low value here. Close to imaginary axis, that I have marked as low value, and this is this S plus 2 is I am considering medium value, and here 0.2 I am considering as low. Okay, and then you can calculate in the similar way. You can calculate that HS will come out to be, just I am writing here, but you please check it. HS plus 1.63, and then KS will be your S plus 5.4, and your QS will be 0.813 into S plus 2. So this is your for case 2. Now for case 3, another case I am considering. So different case I am considering just to see the impact of Q hat on the loop behavior and the system behavior, so that as a designer we can have some idea on choosing given a plan, and we can have some idea how to choose Q hat. So case 3, this is case 3. So case 3, suppose I will choose a case 3 I will choose a large, that means Q hat equal to S plus 20, that means little bit medium. So here I will say this is a large value. So here I will choose Q hat S equal to S plus 20, that means that is large value. That means 20 is now large, far away from the imaginary axis. In that case, what will happen? So then you can similarly you can get that HS will be equal to here 24 point. Now you see the control gains are increasing. So compared to these values, the control gains have increased. So here control gains will be more here in case 3. 61S plus 16.26 KS is 5 point, sorry, S plus 23.4. So it is very large now, and your QS is 0.813 into S plus 20. So now you see these gains have increased. So what will the impact? Which one is which one you will ultimately choose for a practical system? To know that, just we'll have some plot. then we'll understand, then ultimately we'll conclude which q hat we'll choose, whether this low value of q hat or medium value of q hat or high value of q hat, and what will the impact. So first I will see, I will go to the next page, and I have run the system in MATLAB, and closed loop system, and I have got some plots, and those plots I will try to attach here. So first I will attach image. And then desktop, then where will I go? Where is the attachment? Yes, this is attachment. So here first I will show you the TYR response. Okay, so now you see here, just here I will write TY to R characteristics. So now you can see, so here the this one is for 2 degree of freedom. It is a very nice nice response. Now if the same h and q if you use, that means now if I set, if I see the same closed loop pole polynomial, if I choose, if I want to choose the same closed loop pole polynomial, and 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 then if I obtain the 2 degree of freedom input output response, then you will see these three. That means this is one for very low value of q, this is for low value of q, this is for mid value of q, and this is for large value of q. Okay, so q means q I have chosen so as to have some delta. So you can see, using your 1 degree of freedom, you can never achieve a desired response, because this is because you can easily see, this is because the roots of the h's, everywhere you see the roots of the h's are very close. What is the root? It is very close to imaginary axis. Here also roots of h's very close to imaginary axis, and here also. So that means if you reduce the QS, this it is become the roots of H is becoming more closer to imaginary axis. So that's why it is causing more picky response in case of 1 degree of freedom control. So that means, what is my observation here? Observation is 2DF response is independent on choice of QS, QHS. Second, 1DF response becomes picky because of the root of HS close to the J omega axis. So this is the disadvantage of 1 degree of freedom control as far as response is concerned. So so whatever value of QS you will choose, so you can never achieve the response like a 2 degree of freedom control. Okay, the best, that means here the best response that you can achieve, that is this one. But which still have some peak value. So now this is about your tracking performance, superior performance. So what we have shown that 2 degree of freedom reference input to output characteristics is much superior. Now we'll see the what is the response character, the control effort characteristics. Control effort characteristics we will see. So this is my control effort characteristics. Sorry, I should write here T U to R characteristics. What is T U to R characteristics? Now you can see. So the 2 degree of freedom response, the 2 degree of freedom response is only this one. This is your 2 degree of freedom response, and others are for 1 degree of freedom response. And clearly, whatever for large value of Q, for large value of Q, for small value of Q, you can see the peak is more in case of 1 degree of freedom control. And and if you increase the Q, then what will happen? It reduces, but still it is much more than your 2 degree of freedom control effort, peak value of control effort. So this, but 2 degree of freedom control effort, you can see that it is independent of the choice of Q hat. So here, what is the observation then? 2 degree of freedom TUR characteristics is independent of Q hat. As the same thing we have also derived. Second thing is that 1 degree of freedom TUR characteristics is of high magnitude. Is of higher magnitude compared to the 2DF one. So now this is the advantage. So, and you can see this higher magnitude occurs. This is because of that that HS polynomial that is close to the imaginary axis. And in case of smaller value of Q hat, it is much closer to imaginary. So that's why the peak has increased very much. But TU to R characteristics, you see, in case of 2 degree of freedom control, it is independent of Q hat. So if you design the 2 degree of freedom control as following the approach as I have mentioned, then this thing will happen. This kind of advantage of 2 degree of freedom you can easily get. Now the thing is that what so far we have seen, that in case of tracking characteristics or control effort characteristics, we have got huge improvement using 2 degree of freedom control. But now we'll see in case of loop shaping, loop sensitivity approach, or complementary sensitivity plot, or loop transfer function plot, what kind of advantage you will get and whether we'll get any advantage at all. So for sensitivity, I will plot, and then I will also plot the loop, then I will explain. This is sensitivity plot, and then I will plot the loop also. Okay, so now this is your sensitivity plot. This is S plot, and this is your LG omega plot, LG omega plot. This is SG omega plot. I have not written SG omega, so S plot and LG omega plot. Now you can see. So here L1, S1, S2, S3 means S1 corresponds to S1 corresponds to low value of Q hat, that means roots of Q hat closer to imaginary axis, and this S2 stands for medium value, and S3 stands for S3 stands for higher value. You can see the peak overshoot peak is more that S infinity value. S infinity means MS. MS is more in case of in case of Q hat low value of Q hat, and in case of high value of Q hat, what is happening? The MS is less, but in case of medium value of MS, it is traded off. Now in case of loop transfer function also you can see L1, L2, L3. So L1 you can see here in case of low value of low value of Q hat, your loop gain is less at low frequency. Okay, but the cutoff, high frequency cutoff is good at high frequency roll off rate. But in case of higher value of L, you can see loop in case of higher value of Q hat, the loop gain is high at low frequency, but the loop gain is the cutoff, the roll off rate, the roll off rate or the gain at high frequency is not that much less. That means, what is the conclusion? Conclusion will be like this, that if Q hat is chosen, if Q hat is small means here, small means closer, the roots of the Q hat are closer to imaginary axis. That is, the roots of Q hat are close to J omega axis. Then what happened? J omega axis, then what happened? Your J omega axis, then your axis, then your S infinity more, then MS is more. MS is more, number one. Disturbance attenuation. disturbance attenuation is poor. Why disturbance attenuation is poor? No, MS is more. MS is more, and disturbance attenuation is poor. Why? Because here at low frequency gain is less compared to the others. And what about noise attenuation? Noise attenuation, you see, that high frequency gain is less compared to the others. So noise attenuation is better. So now if Q hat is high means roots of Q hat are away from imaginary axis, then what is observation? The observation is, you can see MS is less. MS is less, that you can see from the figure. MS is here less, and then what will happen here also? You can see that that LG omega has high gain compared to the others at low frequency. That means disturbance attenuation is good. Disturbance attenuation is good. But what will happen now? Now you see the loop gain has increased. The noise attenuation is poor. Noise attenuation is poor. So the ultimate thing is that you have to trade off the between the two performance. So if Q hat is if Q hat is chosen medium, then the above performances are above performances are traded off well. Okay, so you can see the disturbance attenuation is also not too poor. It lies in between. So in this way, for a given a practical system, you have to choose your Q hat. Okay. So now we will switch to. So here that means in this design, we'll switch to PID control later, but just now I will explain. So this is first your given given your plan. What is the design approach? Just I am trying to summarize it again. So first a plant is given to you. Then depending on your plant relative degree and the specifications, you have to choose a desired reference input to output model like this, where the relative order of the model should be equal to, at least equal to, here I have chosen equal to the plant relative degree. Okay, so here you can choose greater than equal to, but here I have chosen equal to. So in the reference input output model, also the plant zeros, that means the polynomial CS should be written. At least the right half plane zeros should be written. Okay. So otherwise, your as I said, the 2D freedom controller cannot be designed. Internal instability will occur because of the unstable pole zero cancellation. So in a loop, unstable pole zero cancellation is unavoided. If you do that, then the input output response, you may see that the input output response is nice, but some internal signal will become unstable. That is called internal stability of the system. So internal stability is very important. If you so I will try to say in the next class a little bit about internal instability, but internal instability is nothing but unstable pole zero cancellation in the loop. in a feedback loop, no unstable poles or cancellations should not happen. If it happens, then the closed loop system, then the system will not become internally unstable. Input output response may become stable, reference input to output, but some internal signal may divert. So that's why this RHP zeros, they should be retained. And in fact, here I have retained the CS, total CS, not only RHP zeros, the stable zeros of the plant also I have retained. So then you have to choose Q hat S such that the resulting controller parameters, controller polynomials Hs and Ks will yield some desired loop performances, some desired sensitivity peak, some desired disturbance and noise attenuation characteristics, and then ultimately QS is equal to alpha into Hs. So once you choose this delta S, this Ks, the Ks and Hs polynomial, you can determine using Sylvester matrix approach, or using just by comparing the coefficient of S to the power I of delta S and S to the power I of the right hand side polynomial. So just I am writing here. So here, once delta S is selected, is obtained, the Ks and Hs polynomial can be obtained, can be found using Sylvester matrix approach. Sylvester matrix approach. Sylvester matrix equation approach I have already told you when I taught you that one degree of freedom control design. Okay, so thus the choice of this Q hat is very important, and Q hat should not be far away from imaginary axis, should not be close to the imaginary axis, and how Q hat has to be chosen, that will depend on that is the iterative process. As we have seen here, you have to plot S, you have to plot loop, and you have to see, you have to post check whether sensitive peak is less than 2. The MS should be less than 2 for a good design. Also your disturbance attenuation and noise attenuation are proper or not. Given a filter, suppose WDS or WETAS, in fact you can superimpose 1 by WDS and 1 by ETAS along with your loop transfer function, and you can check whether the disturbance attenuation that condition and noise attenuation condition are satisfying or not. That is also another way to check. So all these things you have to post check here. Q hat you will choose, and then you will post check whether LG omega is satisfying and that robust and that disturbance and noise attenuation and robustness condition or not. Okay. So now we will move to PID controller. So PID controller is also an widely used controller. This is a simple, very simple controller, but widely used in process industry. Okay, so because it is a first order controller, at least in case of single input single output plant, it is a first order controller. So that's why it is widely used in here. So PID compensation, so it is widely used. Just I am writing widely used in industry, in process control industry, mainly process control industry. Why? Because it can be implemented in digital analog fashion, or just tuning, just some op-amps knob you can rotate. You can just tune the three gains are there. Only those three gains, less number of tunable variables are there. The less number of tunable variables has some advantage. That is, you can just change the op-amps knob, and you can adjust the gain. So that's why this PID controller is very well accepted in industry. So widely used in industry. Why? Because of simplicity in structure, easy to implement in both analog and digital fashion. So these are the main advantage. Very simple structure, only three gains are there. So easy to implement in both analog. Using op-amps you can implement, using digital, using embedded processor you can also implement. So that's the advantage. So this is the controller structure. This is the feedback structure. Suppose this is GS, the unity feedback structure. Suppose your CS, and this is your output. This is your output. Okay, and this is your reference input. And this is your tracking error, and this is your control effort. And what is your controller? So controller CS is your PID. So the transfer function is Kp plus Ki by S plus Kd into S. This PID, three gains: Kp, Ki, Kd. Kp proportional gain, integral gain, derivative gain. You can also represent in terms of this is time constant form, 1 plus 1 by TIS plus TD into S. So TI is called proportional time, integral time constant. This TD is called derivative time constant. So this is your PID controller transfer function. This is PID controller transfer function in time constant form. So PID controller in time constant form. Okay. So now what is the what is the effect of closed loop performance on Kp, Ki, Kd? So Kp is called proportional gain. So Kp is proportional gain. So what is the impact? Proportional gain, if you increase proportional gain, so proportional gain, if you increase, then reduces. This will reduces steady state error, but makes the system oscillatory. So here you write, if Kp is increased, then if Kp increases, then it reduces steady state error, but makes the system more oscillatory. That means oscillation will increase. Steady state error will reduce, but oscillation will increase. So that is true in case of any feedback system. If you increase the loop gain, then your steady state error will reduce, but oscillation will increase. Now your Ki. So Ki, what Ki will do? So this is called, Ki is called your integral proportional integral control derivative. So integral constant, integral gain. So integral gain, what will happen here? Integral gain. So if you increase, so Ki increases means ki not equal to 0 means ki increases. So ki, in fact, ki not equal to 0, ki not equal to 0, ki not equal to 0 makes 0 steady state error with respect to step input. With respect to step input, your steady state error will be 0. Why? Steady state error will be 0 because at that time your loop will be of type 1. If the loop is of type 1, then your steady state error will be 0 because steady state error will be 1 by 1 plus ls. Steady state error E by R transfer function. So if the loop is of type 1, then your steady state error will become 0. Steady state error with respect to step input. So that is the beauty of PID controller. If you have a PI or PID controller, then your steady state error with respect to step reference input will always be 0. So but in case of KI makes the system sluggish. Makes the system sluggish. But what will happen? It will make, if you increase ki, integral action means suppose your TD equal to 0, then kp you have kept fixed. Then what will happen? Your what is your zero location of the controller? Zero location of the controller is 1 plus 1 by ti. That means your 1 by ti. So 1 by ti means equal to your no, your what is your pole location? Sorry, zero location. If kd equal to 0, it is kp by ki by kp. So pole. What is your pole location? Pole location is ki by kp. So pole location of the no, zero location of the controller. So zero location of the controller is ki by kp. So if you increase means what you are doing? You are adding additional pole to the system. Additional pole to the system means you will make ti. If you increase ti, integral time constant you are increasing means what you are doing? Integral time constant if you are increasing means you are making the pole. No, ti if you increase actually ti if you increase no, your s equal to origin. You are introducing a pole at s equal to origin, so this is a slow pole, so it will make ultimately system sluggish. It will be difficult to control. That means that mode you have to control, that mode you have to shift. So that is the problem. This will with ki. So I will not write with in keys of this one. I will just write it will make the system sluggish, because anyway. So this is the main implication. It will but makes. This is the main implication, but makes the system sluggish because of introduction, because of addition of pole at s equal to 0. So this is the main reason. So now what is your kd? Kd, what it will do? Kd is derivative time, derivative gain. So what is derivative gain? What it will do? It will increases speed of the response. That means rise time reduces. But if you increase kd much higher to a much higher value to get very fast response, then what will happen? your utility system will be noise prone, noisy system response will be noisy. Okay. So now the tuning of PID parameters. Tuning of PID parameters is very important in industry because how to tune given a plant, how to tune actually KP, KI, and KD, so as to have at least some some response, some desired response. So PID tuning rules are there. So so mainly PID controller is used. So PID controllers is widely used. So in industry, what is happening in process industry particularly, in process industry. So the main advantage, one important advantage, one important advantage, one important advantage of PID controller, PID control is that it can be designed even if the model transfer function, if the model transfer function is not known. Okay, so this is the main, which happens for most of the which happens for most of the process industries. Okay, so the tuning rules, so the tuning rules that are made that are existing for this one, such a tuning rule is your Ziegler-Nichols tuning rules. So the Ziegler-Nichols rules for tuning. So there are some standard tuning rules, some standard tuning rules are there for PID, which makes attractive to the process industry. So irrespective of the model transfer function, so there are some standard tuning rules, and which is seen. There is no mathematical proof, but which is seen to yield very good behavior. So such a tuning rule, the well-known tuning rule that is known as Ziegler-Nichols. Ziegler-Nichols tuning rule. Okay. So what is Ziegler-Nichols tuning rules of PID? First is there are two cases. So one is case one. Case one is for overdamped system. This is for overdamped system that have S-shaped open loop characteristics, open loop response. So the transfer function you need not to have, but if you know the process process has S-shape kind of open loop response. Like S-shape means like this. S-shape means like this. T, suppose this is your YT. Sorry, I could not write properly. So this kind of suppose response. Most of the process industries, process systems are very slow systems, so it has this kind of characteristics. So then this kind of characteristics can be modeled as, so this kind of S-shape characteristics can be modeled as the plant is modeled as modeled as GS, this is equal to K into e to the power minus LS divided by TS plus 1. So how, where is so from the given SF characteristics, how K, L and T are identified? So we draw a tangent at the point of inflation. We draw a tangent where this characteristic is almost flat, at a point where this characteristic is almost flat, this kind of, although my drawing may not be correct, so this kind of flat, no, even my drawing is not correct, so I have to modify it. So you see here around this one, so here almost where it is flat, so you can draw like this. There is this kind of tangent, point of inflation. So you will draw slope. So this is your, so this distance is your, then this distance is your L, and this point, and suppose this is your steady state value. Suppose this is your steady state value is K, and this value is your, this value will be your T. So T is called dead time. Okay, T is called time constant. L is called delay. So T is time constant of the system, and L is called delay. Okay, so this is first order time delayed model, and K is the steady state value. So K is steady state value. So this is your first order time delayed model, system, first order time delayed model. So that means if a system has SF kind of characteristics, then it is modeled first as first order. The system model is maybe higher order, or maybe it is unknown, but the input output response is known, and the input output response has SF kind of characteristics. Then you can model it like this, and consequently your tuning rules is like this. So what is the tuning rule? Tuning rule is like this. Your controller type, if your controller is proportional, controller type proportional means Ki and Kd are 0. If it is P, then what is the value of Kp, then what is the value of Ti, and what is the value of Td. So P, then this value will be T by L, this value is infinity, and this value is 0. If it is Pi, then this value is 0.9 into T by L, this value is L by 0.3, and this value is 0. And this is suppose PID. In case of PID, this value is 1.2 into T by L, and this is 2 into TL, and this is 0.5 into L. So there is no proof. This is a ad hoc rule, and these rules have been made based on a lot of experimentation, of varieties of process that are having a set kind of characteristics. Then they have reported to literature, and these are working well in industry. At least this is a very good initial value of PID gains for a system having a set kind of characteristics, and then to have, this is a very good initial value. Then from some fine tuning you can one can have, which industrial practitioners do. based on their experience. As we have seen, if you increase Kp, then system will become a little bit fast, but it will become oscillatory. So all the trade-offs can be made, and you can tune so as to have desired response. So this is about case one. That means whose input-output response has a set kind of characteristics. Now case two, it may happen that all the process may not have this kind of characteristics. Then in that case, what will you do? So case two means the system that has overshoot in the response. The systems that have overshoot in the response, in the open loop response. So we are considering that the open loop response is stable, but one is S-set kind of characteristics, that is case one. Another is that its characteristic is now have overshoot. So then what will you do? So procedure set, then what will you do? Set Ki equal to 0 and close the loop. Close the loop and increase the gain Kp from 0 to KCR, at which the system, the closed loop response just starts oscillating. Let the period, oscillating means sustained oscillation. Let the period of the oscillation of the sustained oscillation be PCR. Then what is the tuning rule? Then the tuning rule is like this. Then the tuning rule is controller type Kp, controller type may be Kp. What is the value of Kp? What is the value of Ti? What is the value of Td? So controller type, suppose if it is a proportional controller, the value should be 0.5 KCR, and this value should be infinity, and this value should be 0. Because your Ki equal to 0, that means Ti equal to infinity, and Kd equal to 0 means Td equal to 0. So then Pi, if you want to use Pi controller, then it should be 0.45 into KCR, and this is PCR by 1.2, and this is 0. If you are using PID, then it should be 0.6 into KCR, then this is 0.5 into PCR, and this is 0.125 into PCR. Okay. Yeah. So this is the rule for this Ziegler-Nichols rule. So one tuning rule I have said. So there are some other tuning rules, but Ziegler-Nichols tuning rules are the most widely used in industry as an initial guess for PID parameters. Now there are some other important aspect of PID controller. But the main problem with PID controller occurs because of this is an improper function. This KDS. This is an improper function. But improper function, how will you realize that this improper function? Even if you can use a differentiator to implement this, but it will cause a lot of problem in practice. So how to avoid those problems? So practical implementation. So practical implementation. Practical implementation of PID controllers. So how will you implement PID controller in practice? Because implementation problem arises because of this KDES. So what are the problems will occur? The problems. What are the problems, major problems that will occur in practice? The problems associated with problems with PID controllers are: one, derivative term. The derivative term is what? Derivative term being improper is difficult to realize in practice. This is the major thing, realize in practice. Improper terms are difficult to realize. So even if you use derivative of what's called differentiator, there are also still problem causes that I am saying now. So the pure derivative term, what will amplifies the noise. It will amplify. Okay. So this will cause which will cause what? Actuator saturation, because noise it will amplify the sine omega t. So when it will pass through derivative, it will be omega cos omega t. So omega, if it is a noise, omega is really high value, so very high magnitude signal will pass through the actuator, so which will cause actuator saturation. Okay. So not only that, it also causes, that means pure derivative term also causes derivative kick. It also causes derivative kick in presence of step response. Step reference. In presence of step reference. What is derivative kick? Suppose you are applying a step reference signal. So initially output is 0. Suppose initially output is 0. So when that step reference signal will pass through the derivative part, then what will happen? That the PID controller all are in cascade, right? So when it will pass through derivative, then it will be an impulse. So sudden kick will happen. The suddenly high magnitude control signal will get. So that is a derivative kick that is unavoidable. So this will have sudden. So which causes derivative kick in the presence of step, which causes increases it causes derivative kick in the presence of step response, which derivative kick means what? Sudden rise in control input, which makes the control input to increase, which increases control input suddenly, which increases the control input suddenly. So these are the two major problems. So one is pure derivative term is difficult to implement. Although even if you use differentiator, And if you implement, then what problem will happen? The problem is noise amplification. Noise will not be attenuated at all. And the other thing is the derivative kick. Because of derivative kick, impulse the sudden jerk will happen in the controller output. Control input, that means control input to the plant, that means controller output will have a sudden jump in the response as you change the reference input, step reference input. So how to implement? So how to solve the above? What to do? One is first one, that means this derivative term, problem of implementing derivative term. Just we will approximate s by tau ds plus 1. That means we are making it proper with tau d is much less than td. Okay, so that means tau d is much less than td. So we are adding a very fast dynamics compared to the bandwidth of the system. But this first pole, this pole corresponding to this tau d will be far away from the imaginary axis. It will not cause much problem to the system because it will settle down fast. So you can well approximate s by tau ds plus 1. This is one way. This is one way to avoid this problem. One, and secondly, you can avoid. Second one you can avoid by minor loop implementation. A minor loop implementation. Minor loop implementation is what? Just the derivative part you will put in the feedback side. That means this one. So this is your suppose plant GS, and this is your KP, and this is your suppose KI by S. Here I will put the block this one, KD into S divided by KD by S divided by tau D S plus 1. Okay, so tau ds plus 1, and this is your output. So this is your reference input. So this is pi part, this is your approximate derivative part. This is approximate derivative part. Okay, so this is called pi dash d control. Okay, so pi dash d controller. So why pi dash d controller? Because pi part and d part are separated. So it is called minor loop implementation. So it takes care of both. Both noise amplification problem as well as derivative implementation problem. In fact, here sometimes we add one n to make much faster this one. So n is greater than 1. So some tau d is chosen, and then n is made much greater than 1 depending on requirement. How much if if you make, remember that if you make tau d by n, that means this one much smaller, then again it will be 10 to pure derivative, then again noise will get amplified. So you have to trade off how much noise you can that means how much noise you want to pass. What is the bandwidth of the noise you want to pass? That will, based on that tau d by n, you have to choose. So and if you choose tau d by n more, then what will happen? Then again this tool will affect the system performance, system behavior. So that's the trade-off we have to make. So normally here n, if you choose n equal to 1, then tau d is chosen 0.1 to 0.05 to 1 0.1 times of td. Then much less than the derivative time constant, 0.1 times at least. Okay, so this is about PID controller. So one thing just I want to say here, that PID controller I have here designed using Ziegler-Nichols method. There are some other methods. In fact, pole placement control is you can also apply for PID design. So just I am writing here, just apply pole placement method to design PID control for a second order system. Suppose your say GS equal to B2S plus B1 divided by S square plus A2S plus A1. So here you can easily see that if you add a PID controller, then what is the closed loop pole polynomial? Closed loop pole polynomial will be third order. So in PID, how many tunable parameters are there? 3. So you can achieve pole placement. So note, complete pole placement can be achieved. Complete pole placement can be achieved here using PID control. So for second order system, okay, if you want to design a PID controller, you need not to use Ziegler-Nichols and all those things. Because complete pole placement you can. This is a very interesting result. You can generalize this for others. So other CMOS system and all these things. In control system engineering design course, design sessional, you will see all these things. Okay, so of course there are some conditions. So that I am giving it as home task and do yourself. Okay, so that you do on your own. So I am not expanding it. So just now I will just go through once again if there is any major error. Minor error I can point out later. You also will point out. Then I will wind up. So this is the syllabus up to today's class. You should consider for your class test. Class test that will be held on the coming Friday. So that means up to this this design. That means design portion is over. So next class I will start digital control. Just once again I will see. So here this is also important. M equal to n minus 1. Whether it is 1 degree of freedom control or 2 degree of freedom. Minimal controller is m equal to n minus 1. So the design of Ks and Hs polynomial are same as 1 degree of freedom using Sylvester matrix based pole placement approach, or you can directly just for low order system, you can just by comparing the coefficient, you can also obtain the Hs and Ks polynomial parameters, as I have done here, for example, system. For the example that I have considered, I have not used Sylvester matrix. I have just compared 1 and 2 equation. Coefficient of s to the power 3, s to the power 2, s to the power 1, and s to the power 0. And then you have got these parameters. So the choice of Q hat will play an important role in design of 2D freedom controller that I have explained using these figures. So PID controller, after all, it is a very simple controller, but the design, although here Ziegler-Nichols tuning rules and all these things I have shown, but it is just an initial guess for for designing PID controller. If it is a stable system, but if it is an unstable system, then how will you design? Then in that case, your pole placement method, as I have told here, that may be of help. This method, and during implementation is also is an important issue of PID controller. You have to implement like this minor loop implementation. Okay, otherwise you'll be in trouble. Minor loop implementation of PID controller. Okay, thank you very much.